Very excited to introduce Jitendra Malik, who's synonymous with computer vision and probably soon robotics as well, if not already. He's also synonymous with Berkeley. He's been on the faculty there for 40 years, apparently, which is incredible. And, I started to prepare this, memorize this long list of awards, which just suffices to say he's won all the awards. And he's like fellow of everything, and he's in all the academies. But maybe the most impressive is just the number of students that he's graduated. So he's 80 plus PhD and postdocs, and who are now at many of the top universities around the world. So really kind of strong influence on the field. So what I thought I would do is basically talk about maybe one example of a student, kind of one data point on those, all those PhD students. And so here's the data point. He is the academic grandfather of the godmother of AI. So I think that makes him the academic grandfather of AI. So that's pretty cool. So on a personal note, Jitendra and I started at Berkeley around the same time, actually. I was an undergraduate, and he was a professor, and I took probably one of the first classes that he taught there, which was Introduction to AI. And really, I think the only thing I remember from that class was that AI is search. So I think today he'll give us an updated view of AI. We'll see whether it's changed in the last 40 years. All you, Jitendra.
Thank you very much, Steve, for this kind introduction. It's a pleasure to be here. So I'm going to be talking about robot learning with inspiration from child development. And I mean, today is the era of AI. You cannot open the newspapers without reading about various benefits or fears of AI. So I want to talk about AI, but I cannot talk about AI without talking about natural intelligence, because after all, the term was borrowed from the biological version. And I start with this slide because this is like my credo. In sort of medieval Europe, you had to declare that you were a good Christian because otherwise you might be burnt at the stake or something. So these are my beliefs. So my belief is that you have to think about intelligence as a biological process. It started about, 550 million years ago in the Cambrian explosion, where you have the first multicellular animals and they could move. And moving gave them an advantage because then they could find food in different places. But for that they needed perception because they needed to know where to go for the food. So this cycle of perception and action, or perception and locomotion in that case, is the beginnings of intelligence. And you can think of the brain as something in between, which connects perception and action. And there's this line from the psychologist called Gibson, who's one of the eminent figures in human vision. We see in order to move, and we move in order to see. Okay, and now we jump ahead a few years, we can get to the development of the hominid line, the place where humans split off from other primates. And a very key thing there is the emergence of the hand and manipulation and tool building. And there is this, the fossil record shows that actually the development of the brain follows the development of the hand. And this was very critical. And this all started with bipedalism. Once we could walk on 2 feet, then the hands were free for tool use. And then in modern humans, maybe it's 100,000 years, maybe it's a couple of 100,000 years, maybe a million years, is somewhere when language develops and you have abstract thinking and culture and all the rest of it. So the important point that I want to make is if you think of the journey of intelligence as 24 hours, language and culture in the modern sense is more like the last few minutes, 5 minutes of it. Now, the way AI has actually developed today has kind of been backwards. Our biggest successes are in language, whatever is the last 5 minutes of this. And that's great. And it's remarkable, and we should appreciate it and capitalize on it. But I would like to argue that actually the 24 hours minus the 5 minutes is actually very important. And in fact, from a practical engineering point of view, in terms of helping humanity, what we could call robotics, which is the connection of perception to action, is going to be critical. And okay, so what are the central problems of robotics? So I got into the field maybe 6, 7 years ago, or maybe more seriously only 4 or 5 years ago. So when you come from the outside, you sort of have to have a sense of what are the important problems of the field, and you could be wrong, but you have to make some assessment. So this is my belief that, okay, these are the central problems of the field: locomotion, navigation, and manipulation, because everything should go in threes. So these are the three that to pick on. So what I'm going to do is start with just like a flavor of where we are today, and I'll pick work from my group on each of these dimensions. What can we do today? So let's start with locomotion. This is, of course, biologically the most important capability. We see in order to move, and we move in order to see. And I'll show you some results from our group. So this is what we can do today. This is humanoid locomotion. We have previously worked on quadrupeds and so on, but humanoid locomotion is harder because 2 legs balance is harder. And so this is a robot walking around for people who know San Francisco and the Bay Area, this is around there. This is in the city. And here's a slide which shows this robot walking around in various hiking trails around Berkeley. So this is the state of the art. I mean, there are many companies which are building humanoids, but in terms of just walking behavior robustly in a wide variety of conditions, this is what we can do today. Okay, let me talk about navigation. So this was also very important because navigation means go to somewhere for a certain. So you could go to a certain geometric location, or you could go to where the food is, or in the case of a robot in the home, it could be go to the kitchen, or go and pick the teddy bear on my son's room lying on the carpet, whatever. So I'll show you results which we presented at RSS this year. So we call this model GOAT, go to anything. Okay, and the idea here is that you can specify a goal in some form. So the goal could be a chair. A goal could be a teddy bear. A goal could be a location like a kitchen sink or toilet or whatever. So you specify the goal in some way by language or with a photo or something like that. And then the robot has to get there. And the way we did this experiment was that we rented Airbnbs, and we put the robot inside, and the robot is then given a task: go to the TV or go to the potted plant, and it has to do it. So it has to build whatever representation it does, a map of partial map of some sort. So what you see pictures are pictures of that. So in one corner you see the goal. So this is what so there's this robot, which is, you can have different platforms here. It doesn't matter. This is the Spot robot, but it could be on any robot. So what does it see? That's what you see as the observation, and then it's given a goal. So the goal here is, I think, the kitchen sink. You can see that photo. So what it has to do is start from where it is, move around, explore until it finds the kitchen sink, then declare success, then you give it another goal. So you'll just see various rounds of that. And at the bottom, you'll see a list of the objects that it has detected, as well as built up a map. So this is what it says. It starts out not having much of a map, but then it'll start to move. So it's not yet found the kitchen sink. Then suddenly it will find it, and then, okay, success. Then it goes to the next goal, which is the lion teddy bear on the foosball table. And then it's found that. Then it's going for the red cup on the brown leather chair, and so on. Okay. So these are examples, and we have tested this for like 200 different targets and in 10 different homes and so on. Okay. So this is navigation. Okay. Yeah. So okay. Next, what can we do in manipulation? So in manipulation, I'll show you some results from this recent paper, which is on arXiv. And here we have a bimanual setup. So again, the robotics community works a lot with parallel jaw grippers, and for many industrial tasks, they are adequate. But I personally believe that the future, if you want home robots, has to be multi-fingered hands with tactile sensing. And so they are a pain to program, but I think our techniques today can do that. So these are results there, which have been trained in this currently very popular paradigm, which is you collect some demonstrations with teleoperation and then use that to train a policy. So let's see what we can do. So this video is real time, and okay, so these are examples of tasks. So some of this, like picking up 2 bricks, you couldn't do with a parallel jaw gripper. And this hand is a prosthetic hand. It's actually sold for people who have lost their hand. Okay. How are the tasks specified? The task is programmed. So you have said this is so each of these is a separate policy. So there's a separate policy for separate tasks. Okay. So now let me take a short quiz. A person who is not allowed to answer is Dieter Fox, okay? Which is, how close to solved are we? If you look at these videos, like, I hope you are impressed, but the question is, how close to solved are we on these 3 tasks? Which of these looks like, okay, looks like it's done, okay? So, okay, which of these do you think is the easiest or closest to being solved? Okay, navigation, yeah, that's the right answer. Which is the hardest one? Okay, so this is a smart audience. Everybody knows the answer. So yes, so this is my way of thinking about it. Navigation is kind of nearly done. In fact, I think of navigation as mostly a computer vision problem. So it's the most friendly problem for computer vision people to get into robotics, because SLAM, structure for motion, it's basically the same game. So we know how to play this game. So locomotion, I feel that there have been very impressive results in the last 4 or 5 years. In the past, there was locomotion done by developing controllers with a lot of clever design, like Boston Dynamics did, but they need like 19 different controllers for 19 different situations. Here is a learning-based controller where one controller works for all these different situations. And then in manipulation, I feel that we have a long way to go. And this is the bottleneck. If you want your home robot, the reason why there isn't a home robot you can buy today, which will do useful things, is because we are like maybe 20% of the way of solving the manipulation problem. And you should think in time frames of 5 years to 10 years. Whereas locomotion, I think in 3 years, I mean, I don't know whether you will have James Bond-like parkour movements yet, but we can do well, okay? So why? So why? I mean, the average person in the street will think that, given what the advances there have been in language, how come we are so far behind in robotics? Okay, and my general take is language is the most advanced, computer vision is in between, and robotics is furthest behind. And why is that so? I mean, the big challenge here is data. Okay, and it's much harder to obtain for language and vision. Essentially, the internet solved the data problem, right? Because people were uploading books and texts and so forth, so the training data for language people was readily available. 1 trillion tokens are there on the web. In the case of images and video, also that happened, right? There is 156 million hours of video on YouTube. And I was talking to Steve earlier today. There was a workshop that he organized on internet vision, and that was then a newfangled thing. That, look, there's all this, there might be vision data on the internet, and we could do something with it. And that was way before deep learning became popular, but clearly that was actually a prerequisite for that success. Now for robotics, the ideal data would be, I mean, if you had robots which were anthropomorphic, would be data of like my neural activations when I decide to do something, all my joints, all my muscle activations, and you record that over time. And now we have all those trajectories uploaded to the web, and we use those for training a robot. Even then, the robot has to be anthropomorphic. If it's a different embodiment, there's a challenge. So we don't have that. We are not going to have that. And this is I think at least if you have to give one reason, then that's the reason. So, okay, so that's what we have to do. So that's the challenge for us. So how should we go about doing this? So I feel we need to be a bit cleverer than what so now when I'm saying we, I'll act as if I'm a roboticist, okay? We have to be cleverer than the language people and the vision people, because we may never have that amount of data, okay? So the language people have these great models like GPT-4 and so on, but if you compare the amount of data that they need compared to a human learner, I mean, the estimates vary, but if there are estimates of how many words a child learns per month, or hears per month, not learns. And then you're probably off by 10,000 or 100,000. I mean, Luke here, hopefully he doesn't disagree with those numbers, right? Something like that. So 10 to the power 5, we are off. Our models use way, way more data. Okay, so if we were smarter, we would be better off, right? So we'll need data anyway, but we should be smarter about it. So then there's a question of how you go about it, and personally, I'm betting on this paradigm. So this is the paradigm of learning from child development. And actually, the person who proposed it was Alan Turing, I mean, the founding father of our field. And he has this in this 1950 paper, he says, instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. So this is 1950, so this is like 75 years ago. And Turing actually knew nothing about child development, in fact, because there were a few people like Piaget who had worked already, but Turing never quoted any of them. I'm not sure if he ever read any of those papers. But of course, in the last 75 years, our colleagues in psychology have made major advances, and they know a lot more about how children learn. So it's not just like people speculating on the basis of what they observed their kids do. So here is a slide from a paper by Smith and Gasser. And I mean, there's a huge literature. This is just meant to be representative, that these are aspects of how children learn. Multimodal, which means audition and vision and touch together. Incremental, meaning that you learn in stages and a following stage builds on the previous stage. Physical, so you actually interact with the world, you explore. Social, we learn from others. Language, which comes later but is very crucial. So these are, and there's more detail than that, I mean, about every stage. So my research philosophy is, let's take inspiration from this, and if we can, this will first, if we succeed down this path, we will build physically embodied robots. And then we might have a path to using or needing less data. But I'm not going to be absolutely faithful to the biology. After all, this is an engineering goal, but we will take inspiration, but we'll be willing to ignore biology when necessary. So, so that's the framing of the research enterprise, which we have pursued for a few years in my group. So I'm going to start with an old paper from like 2021, but it captures actually the philosophy very well. So this was work on quadruped locomotion, so four-legged animals. And the starting point when we got into this was, okay, gaits. I mean, animal gaits are well known. But instead of just looking at that, and this was used by people like Mark Rabert and people at Boston Dynamics. They looked at this literature and they were inspired by it. Even some of the people who use learning, like Marco Hutter's group, they start from a gait and then they develop a residual policy around it. Whereas what we thought was, okay, let's look at what the child development people do. And there is an expert called Karen Adolph at NYU, whose group has done a lot of work on observing how children learn to walk. And I mean, there's a whole body of work, but I'll just show you this example. So there's this girl who's just about learning to walk. And just observe her movements, right? Okay. So what you should notice is that she takes a few steps. Some are sideways, some are going forward, some are going backwards. And Here, they'll be annotated. So S means sideways, F means forward. So now, so this is the annotation, and let's play it. Right? Okay, where is the gait here? This is not a walking gait. This is not a running gait. This is, so Karen Adolph's term is bouts of steps. Okay, so this is, gaits do emerge later. So if you are an Olympic runner, I mean, you have a very, very efficient gait. But that's not how you learn to walk. You learn to walk in this steps of, I mean, and there's a knowledge of, you learn to stand, then you learn to take steps, then you start to take steps which are more safe, and then they become more efficient, and so on and so forth. Okay, so that was a key observation for us. So we wanted to have a learning approach which would work tabula rasa with no gaits built in. The second insight was that, which is for me coming from pattern recognition, was that in robotics, it's as much about generalization as it is about adaptation. So in computer vision, the key problem is generalization. You have to recognize a dog, even though the dog looks very different, and there are different breeds of from different viewpoints, and then there are different breeds of dogs. In robotics, you have to think about control, and control means being robust to perturbations, and you also need the idea of generalization really means adaptation, adapting to different terrains. So if you want your dog to walk, it should walk on grass, it should walk on sand, it should walk on hard ground, etc., etc. So we developed a machinery for this, which again, the details are not so important, but basically it rests on, so this policy here is what is issuing the commands for the robot, so all the joint angles. So that's the action vector, A sub t. This is sort of the reinforcement learning terminology. And then there's this Z, which is like this latent vector. And this is in some way encoding for the environment. Like, are you in sand? Are you in hard ground? And so forth. And nobody tells you what that is. You have to figure that out in context. And you can figure it out from your past history. So as you're walking, then when you apply the same forces, if you are in sand, your foot will rise a shorter distance than when it's on hard ground. So that's what is shown by this adaptation module. And basically, we are training with reinforcement learning in a simulator. So think of that as just a fancy form of trial and error, basically. But you want the policy to vary depending on the physical circumstance. And that is captured by this adaptation module. And this also is trained in the simulator. And that's it. And I'll give you one demo which illustrates what's going on here. So here's this robot which is trying to walk on this mattress. But if you look at the feet of the robot, there's some plastic there. And then we are going to pour some oil, olive oil, paste some olive oil on this mattress. And then the robot is going to walk, and it's going to slip a bit, and then it'll recover. So let's see what happens. So you notice this period when it's like having trouble, it might fall down, but then it manages not to fall down. Okay? So now when you see this in slow-mo, what you have to look at is that there are these two variables, z1 and z5. These are components of that vector z. And essentially, they change with as the robot moves. So basically, initially, the robot's policy is wrong. It's for flat ground, not for slippery ground. As the z gets estimated, the policy gets better. And then with this idea, with this kind of training, we were able to develop a robot policy which was trained completely in simulation and then put out in the real world, 0 shot. And then these are the results. And whenever you have a reinforcement learning paper, people always like to point out some emergent behavior. And in reinforcement learning, you do get emergent stuff. So for example, the dog figures out that it taps its foot on the obstacle, and then it keeps tapping higher and higher. So essentially, this is a blind robot. So, but with that, you can figure out how high the obstacle and how much to raise your leg. And these are more examples. Okay, and then later on we built and this was a blind robot, and of course blind robots can walk because blind humans can walk, so it should be possible, right? But what do you need vision for? You need vision for difficult conditions. For example, if you want to cross a river on stepping stones, then it would be good to have vision. And so we trained a robot for that, and I won't get into the technical details, but just show you the final demo. And so this is from 2 years ago, but it shows like quadruped locomotion we have solved, I think. So everything is on board. There's a camera on board. There's computing on board. It was trained in simulation, 0 shot. It doesn't know what's the scene in front of it. Whatever it sees is what it observes. I think the demo works better because the dog's struggling. So we have this psychological sense of identifying with it. Okay, so anyway, this is quadruped locomotion. Humanoid locomotion or biped locomotion is harder, and I'll give you more examples. But now let me. So this was an example of insight coming from looking at the literature on child development. That you can make it fully learning based, for example, and you need to have trial and error. Actually, Karen Erolf has these studies which show that children in fact fall a lot. So people criticize reinforcement learning that, why does it take so many trials? Actually, human children, when they learn to walk, they fall a lot. But because they have soft bodies and low center of gravity, they do not hurt themselves as much. When you're 85 and you fall, it's a different story than when you are 8 months old or 1 year old. Okay, but multimodality. So let me talk about that. So multimodality means multiple senses. So there's another meaning of multimodality, which is in the statistic sense of having multiple modes, but that's not what I mean. Here, multiple modality means vision, audition, tactile, things like that. Okay, so this is a project which was on manipulation task, and here what we were trying to do was to rotate an object in the hand. And it turned out, we had worked on it before, but when we constructed harder versions of the problem, like rotating about arbitrary axis, the only way it would work was by making use of both vision and touch. And so the vision is this, you can see this camera, this Intel RealSense camera, and you can do standard computer vision processing of segmenting out the object. But the touch part is, if you see these fingers, there's some tactile sensor there. And this was something developed inside Meta, which was, I think today it's public, so you can read up about it, this sensor called Digit 360, which is a very fancy tactile sensing device, which is very accurate and can measure the forces applied to the fingers. Okay, so we used this, and then these are the results. So what you see here is the generalization behavior, which is you can rotate many different objects, and different rows correspond to different axes of rotation. So the rotating about the vertical axis is the easiest version of this task. About x and y axis is harder, but let's see what we can do. And the way this was done is a similar architecture to this, to what we use for walking robots. If you will, a robot is walking on the ground, so those are 4 legs walking. When you are rotating an object, it's 4 fingers walking around and on an object, right? there's some analogy you can make, and this idea of rapid motor adaptation actually applies here. But you can see the generalization here. And then, okay, the details of how we did it doesn't matter. It is again trained with reinforcement learning in simulation, and then transferred zero shot to the real world. This is the policy. But this is the figure that I think is the biggest lesson here. So this is on the y-axis is performance. Performance here could mean how long can you rotate before the object falls down, for example. So on the right is a policy which has complete knowledge of the true state. What is the shape of the object and what is its pose. So that does the best, obviously. And then on the left is where you don't have any knowledge other than proprioception, just the joint angles of the contact. And then the second bar from the left is what you get with just use of vision. The third bar is what you get with the use of touch. And the fourth bar is vision and touch together. And vision and touch nearly gets you to perfect knowledge, the performance with perfect knowledge. Now, I think that in the robotics community, touch has been neglected. But there's a good reason for it, because tactile sensing is not yet mature technology. It's not like computer vision. Everybody who has a cell phone has a camera inside it, and it's like costs $5 and it just works. Tactile sensing is not like this. But I believe that tactile sensing is going to be critical to the success of robotics for, like, say, home robots for a very wide variety of tasks. You may be able to get 75% performance without touch. But if you want it to really work at 99.9%, you may need touch. That's my belief. So sometimes there are these arguments where people say, oh, but I can do this with a parallel jaw gripper. Yeah, but you will do it right 80% of the time, and I need it to be 95% of the time or 99% of the time. Okay. So this is a good lesson for multimodality. We always have multiple senses. So when a child is lying in the crib and playing around, you can see that kids, right? They put objects in their mouth, they're touching them, they're hearing the sounds, everything. It's vision, touch, hearing. Everything is being activated at the same time. Why should we deprive our robots of that wonderful experience, right? Okay, I'll give you another example of multimodality, and this was in the context of learning to walk and how to learn to use vision. And this was a pretty example because for people who are in the machine learning business or computer vision business, we like the idea of self-supervision. So as opposed to external supervision. So external supervision is you have a bunch of images and you have some human say, this is a dog, this is a cat, this is a zebra. Self-supervision is when it's all there in the data and you don't need human annotators. And in language learning with next token prediction is an example of self-supervision. Here, there is a form of self-supervision where one sensory modality helps supervise the other sensory modality. So let's look at this. So look at this robot. It's walking, or it's standing right now. And you have its proprioception, which means that all its joint angles. From the joint angles, you can do the math, you can do the inverse kinematics and so on, and you actually can figure out how much above the front legs are with respect to the rear legs. That can be worked out from just the joint angles. Okay, now what we want is to train the vision system. The vision system needs to know about depths, because if the robot is going to climb stairs, you need to know implicitly you need to know the height of a step, right? But how do you train it? The vision should work in advance. Without me being there, I should know how high the step is. So the answer is simple, just wait. When you get there, your proprioceptive system will know. So the vision system can be trained from the proprioceptive system with a time lag. So this diagram will try to show that. So you have the proprioceptive system, which knows the height of the front feet relative to the bottom feet, okay? And the vision system wants to predict that, okay? I zoomed over the slide. So now what we actually did was we trained our robot this way. It walks, and then it acquires this experience. So in the first day, it is terrible, okay? And what we'll do is we'll give it this, but when it is terrible, it still acquires the experience which trains up the vision system. So on the second day, its prediction system from vision is better. So it'll walk better. And the third day, it'll walk even better. And what you will see are some examples of it walking on day 1, day 2, day 3, and the error rate going down. So let's see if that happens. Okay. So that's day 1. Not very good, but collected useful experience. Day 2, and on the right you can see that the success rate is going up and the error is going down. So now it's earned a PhD in walking. Okay. So, so this is the moral here is with multimodality, the senses can supervise each other. And my previous example was that with multiple modality, you can do much better at the task of manipulation. Okay, let me give another example. So this is for incremental. There's been a lot of fashion in machine learning, robotics of end-to-end learning, where any task you try to learn end-to-end. I don't fully like this because I cannot do end-to-end learning of the task of going from, coming from San Francisco to Seattle. This is a task with many levels of complexity, and you really want it to be hierarchical and so forth. So hierarchies should be used to make planning easier. So here we decided to do a task which was building on top of the fact that our quadrupeds can walk. So basically with our dogs, we can say, go in this direction at this speed, and then it will go at that speed. So the leg movement is taken care of. So we decided to do a higher level task, and it's what is called a pursuit evasion game, but it's better explained by this figure, by this video. So you see what's happening, okay? So this dog's chasing after the woman. The goal is to catch up to her, okay? So you can think of it as play, or if you are militarily oriented, you can think of it in other ways, but I prefer to think of it as play, okay? So now you'll see that essentially it detects her and it wants to catch up to her. But there is smart behavior needed here. For example, you don't go to where the person is now, you go to where the person will be. So you have to learn prediction and so forth, right? And all of this emerged, and what we did was we trained this in simulation, but at this higher level of this pursuit evasion game. And so the behaviors which emerged was chasing, seeking behavior. So if you don't see the other person, you look around, you turn around until you find the person, and so forth. And it was, if you try to train it end to end for this task, starting from joint angles for walking, it would not work. The search would be too high. So the moral of the story is, let's have hierarchical planning and control are classical good ideas, and they should not be forgotten. We should continue to follow them. Okay, but this fits in with the spirit of incremental learning. Okay. Be physical, explore. I think that's permeating through all these examples. The use of sort of search and learning techniques. These are all about exploration right? Okay, let me talk about social learning. Social means learning from others, and a child learns from the caregivers. When you grow up, you learn from your peers, you learn from your teachers, and you're always learning. We are always in a social context. Culture is just the accumulation of social learning from generation to generation, right? I mean, this is intrinsic to humankind. So how do we use this? You can use it in various forms of imitation learning, and this is again an idea which goes back many, many years. It's just about how to implement it. So the first example that I want to use is from Berkeley, like the many Berkeley faculty on this paper, which was we start from YouTube videos of this person doing cartwheels, and then we make the Atlas robot do the same. And there is an embodiment gap, right? The human body doesn't have the same weights and masses of the different parts as the robot. So what you do, though, is that you can make the so the robot is going to learn with reinforcement learning in a physics simulator. But you can make the job of the robot easier because in every frame you give it a target pose, and the target pose is derived from the human. And what you do is you use computer vision techniques to extract the poses. So this was a preliminary work on this going back 2018, and we call this skills from video. And I think I really like this agenda, and this brings together, like, for me personally, all the computer vision kind of technology and then applying it to robotics. So I'll give you the most recent example of this, this is a paper which I showed some results in the beginning, and this is going to be presented at NeurIPS here. And this is humanoid control as next token prediction. So language people have gone to town with this idea of autoregressive modeling. I mean, it actually goes back to Shannon's paper from 1951, where he estimated the entropy of English by asking his wife to predict the next word in some text that he was doing. Okay, so here, the next token here, of course, refers to motor commands. And so basically, we'll have a transformer, and then we have some tokens which correspond to sensory input. This is still a blind robot, but the input here is joint angles and so on. And then there's a desired command, which is desired angles. And we'll have a bunch of trajectories. And these trajectories will come from different sources. So some may come from some other previously trained policy, like from reinforcement learning. Some may come from observation of some YouTube video. And those trajectories will be incomplete because you do not know. You know the observational state is the joint angles at every moment. You do not know what the human was commanding, right? So you don't have access to that. So okay, that's missing data. I mean, statisticians have dealt with missing data. We can deal with missing data in these paradigms as well. So this is the flavor of it. So here we have some examples of videos. So like, okay, this guy there's some YouTube video. And now you can retarget it to the robot. The anatomy is slightly different. And then throw these trajectories in the mix. And anyway, with the help of all this data, we trained this humanoid locomotion policy. I think I showed this video already, so I'll go and skip this. So I think this is just one example of the power of imitation learning, which is that you learn from observations of others. Now, I don't believe that this can be the full answer, because if you are learning to tie shoelaces, or you're learning to use how to use chopsticks, I will show you, but you have to still do something in your own body. So, but my general conjecture is maybe 90% of the data can come from observation and 10% from interaction. Whereas if you do vanilla reinforcement learning, you'll spend like billions of trials just getting to pick up the chopstick, right? Okay, now let's go to manipulation, which I think is the final frontier here, because I'm very bullish on the state of the art in both navigation and locomotion. But in manipulation, I feel that the problem is hard. It will take us years. I think we have perhaps this tendency to see some new results and then say, oh, wow, this problem is going to be solved with this paradigm. I think there's a long way to go. So I showed you those results in the beginning, which maybe you found impressive, of this picking up this wine bottle and so on. But the questions to ask are, how often did that work? Did it work 20% of the time? Did it work 99% of the time? Because I can always find some demonstrations which are effective. How versatile is it? How much design effort was needed for each task? So once you think of it all this way, you realize that, okay, there is a lot of research to be done. Okay, so but let me get into what I think imitation learning has to offer for manipulation. So this is the dream. The dream here is you have some video of people, like, okay, this is somebody, in their kitchen doing something, and what we can do is we can 3D-fy the scene. So 3D-fy means 3D-fy the hands, okay, and 3D-fy the objects. And imagine that the computer vision has to deliver on this, and it cannot fully deliver on this. But imagine that computer vision delivered on this. Then you could take 156 million hours of YouTube video, and you would have a lot of training data for lots and lots of activities of daily living and not so daily living. Cats. You would have lots. Certainly for training a robot cat, you have lots of data. So that is the dream, and we are not there yet. But let me show you what we can do. Okay, so we can do the 3Dification of hands part, I think, is in pretty good shape. Let me show you some results where, so this is a paper we presented. You can download this model and use it. In fact, lots of people are using it for, if you want to do a task where you want to copy a human doing an operation, and you can 3D-fy the hand by the model we have here. This was presented at the CVPR. Okay, so it's being done frame by frame. There is no use of temporal continuity, which could smooth things up. The top left is what the input is. So each frame, the hand is being detected, and it's being lifted to 3D. Okay. Okay. So it's relying on having a parametric model of a hand and then a lot of data. Okay. Okay. So, this is just meant to show the variety of poses and complexity with hands which are entangled with each other, and the system still works. All the corresponding to all the joints, all the degrees of freedom of the human hand. It's called the Mano model, M-A-N-O. There's a SMPL model for the whole body and a Mano model for the hand. So these are examples of hands interacting with objects. Emission rigging. Okay, I had to include this, right? Okay. Okay. So, and this is perhaps the more useful part. Can we learn about how to use scissors and so on? Okay. Now, this is going to be noisy data. It's going to have certain things missing, but the point is there is no problem of big data. There is lots and lots of it is available. So we have to find a way to use it, and I think we will. The computer vision for this has to be completed. Okay, so so as I said, the hand part we can do. The object part is challenging. Let me show you what we can do. So this is a very recent paper. And what we do is, okay, let me just riff a bit on 3D. So of the various problems in computer vision, 3D reconstruction is the most classic one because it in fact precedes computer vision. It was there in the field of photogrammetry. It's existed for like 150 years ago. There are papers from people like Krupa around 1900 and so on. But what we humans can do, we have this remarkable ability that we can see 3D even in a single image. And the reason why we can do that is because of a lot of prior knowledge which we have acquired by seeing the world from multiple viewpoints. Okay, so eventually, this should be encodable in our big neural network models. It'll get there. We just have to get it there. And so this is work which connects to a model which I'd worked on with colleagues at Meta called MCC, which is like this. Okay, I don't know whether. Okay, so that enables you to do generic 3D reconstruction, but here we do reconstruction in the context of the human hand, which provides a scale for the object, because the hand is always the same size. And then these are examples of, again, I think that I'll skip the technical details, and these are these obligatory tables you have in papers which show that my row is darker than your row, okay? But here are some results, okay? Okay, so this is the hand and the object reconstructed. And you're seeing this from different viewpoints to show the 3D nature of the reconstruction. Is this like done? No. This will take a few years before it becomes really good that you could just run it on 156 million hours of YouTube videos or Ego 4D data or whatever. But when it gets done, I'm not saying if, but when, okay, when it gets done, you will have the big data needed for robotics. And that combined with the ideas that we have of using reinforcement learning, where the big data is easy because the computer produces that, I think that these are some of the steps towards solving the grand challenge of robotics. Currently, a lot of attention is being directed to collecting trajectories with teleoperation and using that. And I think that will be part of the solution, but at least in my view, that will not be the full solution. And with that, and with the hope that in a few years we'll have made much greater progress in robotics, I want to end. Thank you.
Well, thank you very much, Jitendra. Questions, I think. Start out over here.
So you showed a few videos where you trained it completely in simulation, and then you said you went to zero shot, running it on the real robot. So a lot of people, have trouble with that. You didn't say that much, I don't think, about, is that just not a problem for you, or?
No, it requires ingenuity, yes. You need smart graduate students and postdocs. So I don't want to trivialize it. I mean, there are, okay, I'll make an analogy to neural networks, in fact. I mean, 10, 15 years ago, people say, oh, but these things don't work. It gets stuck in some bad local minima. So there is a little art in how to train neural networks. And over time, people acquired it. So there is a little bit of that. I mean, so domain randomization is part of the answer. Okay, I think adaptation and learn is part of the answer. I think we might use some techniques from classical control like system ID and bring them in. We might want to do something in sim, take it to real, go back to sim. So it'll be like an engineering discipline which over time you become good at. So that's my take. It's not, I don't think of it as, oh, there is like this one magic theorem that you will find which will make it work. But it will become better as a result. So that's my slightly unsatisfactory answer, but that's the best I can do.
Start with the person in white.
It seems like you made a lot of use of sim to real for a variety of different ways of getting data for reinforcement learning. So you could do rapid adaptation in the real world. Where do you think at scale the simulation will come from? Or do you think we'll have simulators we can just program that will be sufficiently general?
That's what I believe. Dieter will deliver it. No, but seriously, I mean, you have Mojoko, you have work from NVIDIA. I think the simulators are getting better, they're getting faster, and they ride the compute curve. See, think of what, I mean, this is like Sutton's bitter lesson. When you have something which rides the compute curve, you're well off. So computing, these simulators will get better and faster, right? So people, I mean, yeah, it's hard when to model with soft objects and contact, but actually not, the simulation does not have to be perfect to be useful, okay? And it's not good for everything. I think for locomotion, the advantage is that specifying the task is easy, okay? for some of these manipulation tasks, like how do you slice an onion? How do I specify the task using reward function terms? That's hard. But doing a demonstration is easy. So let's not be religious about it. I think we might use demonstrations to specify the task and use reinforcement learning to robustify the policy. I think all of this is possible. And we'll work it out in the next several years. Yeah.
I'm curious, given how fuzzy metrics and evaluation is in robotics, how do we know when a domain is solved versus not solved? And is there a good way to know, which domains to spend our time exploring?
This is in the eye of the beholder. When I started in robotics, I spent a fair amount of time trying to persuade robotics people that, oh, you should do benchmarks the way computer vision people do it. And I thought I was, preaching to the, the natives, right? I turned out I was wrong. I think that in robotics, benchmarking is harder than in computer vision, and it won't work exactly the same way. But this does not mean that you do not know what approach is better than another approach. I think you need to be good about and honest about your experiments. I think that if you run experiments properly and you reveal enough about the details of your experiments and you are honest, which I think means that you accept that your performance is actually low. So computer vision made a big advance from the 1990s to the 2000s when the performance of recognition systems went from 90% to 15%. It was an advance. I'm calling it, it sounds paradoxical, because those systems which performed at 90% were totally rigged. Okay? They worked because we had totally cheated. When, like the first results on Caltech 101 was 16% performance. That was great because now it was an honest to goodness performance in the wild. So I think that like my struggles with R2 of in robotics is that they think too much about the level of performance. But actually they should be more tolerant of the level of performance because new ideas will turn out to have low levels of performance. Okay? I think you have to, your judgment has to be there. Okay? We should do the best so that we can share results and techniques and benchmarks, but it's never going to be as easy as it turned out to be in computer vision.
All right, one more question. Linda, your hand went up first.
Have we really solved object recognition in computer vision, or are the benchmarks just fooling us into believing that anyone can tell a bicycle from a sheep?
Okay, okay, solved is a loaded term, but I feel that it is solved in the following sense. It's not, at least the standard version of the recognition problem, I would not advise my PhD student to work on it. I would, if there's a very non-standard version or very creative angle, then yes. But I personally, I worked on recognition for like 20 years of my life, or maybe 30 years of my life. But in 2015, I quit. Because in my group, we developed RCNN, then subsequently Rosker Schick went off to Microsoft, and then there were many papers and then subsequently at FAIR, and that group really did it. But it was clear that it needed big data, big models, big everything, and that was the kind of stuff which was going to be done by the companies, okay? And in academia, it was going to be hard to compete on the scaling up front. But you can compete with very new ideas and very new approaches. So I'm not saying that recognition is solved forever in all settings, but right now a lot of the advances are going to happen with the use of sort of scale, which will be done by the companies. And we just have to be very careful in not sending our students off to work on problems where they are doomed to fail, or they're doomed to be beaten by somebody with, like you don't fight a gun with a knife, right?
Dieter, why don't you close us out?
Oh, I just had a question with, so you put a lot of, first of all, great talk, it's always really nice work. You put a lot of emphasis on, let's say, motor skill kind of learning, and then there's also a question, where do then the symbols come from and how do we connect that to planning. Do you have any thoughts on, do you hope that kind of symbol-like or connections to language, that this will emerge from these skills, or do we have to come from both sides where the language then is connected down there? Or
That's a very good question because I didn't even touch it. I had language in one slide and after that I did not mention it. So I feel that that's where language comes in terms of these higher stages of planning and so on. I feel, so if I want to rant a little bit, I feel that today language is being used in robotics in not necessarily the right ways. Because you cannot do robotics without doing robotics. I mean, we have to have the low-level motor skills, and those are in the sensory motor domain. Language is needed for planning and for composing these skills, and like, how do I describe making an omelette? I mean, language is very good. I mean, video is also good, but language is also very good for describing the stages. So language gives that abstraction and communicating the higher levels of the hierarchy. The lower levels of the hierarchy should be sensory motor. The higher levels are language. And we need to respect all of them. And I don't like it when robotics people go chasing up after the shiny new object, which is LLM, and neglect the low-level skill development, because otherwise these will be castles in the air because they will not rest on solid ground.
All right, let's thank our speaker one more time.
Thank you.